Hello friends, welcome to my YouTube channel. My name is Prathamesh. Without wasting our time, let's begin. And if you like, please like, share, and subscribe.
Right now, enterprise architecture suffers from a strict structural flaw. As you can see in this visualization, data nodes are isolated, failing to connect across the network because data sits in one silo while AI models operate in another. Organizations rely on a fragmented stack. They maintain isolated vector databases, separate machine learning trackers, and disparate business intelligence tools that do not natively communicate. When systems require constant manual intervention to pass data from a tracker to a dashboard, you cannot build multi-step autonomous AI agents. The latency and friction break the chain of logic. Databricks designed their 2026 data intelligence platform to solve this exact bottleneck. They rebuilt the architecture to move away from passive environments where models simply wait to be queried, creating an active, integrated ecosystem. In an agentic workflow, autonomous systems are given a goal. They plan the necessary steps and execute business logic directly against enterprise data. To make that level of autonomy reliable, predictive, generative, and conversational AI must be collapsed onto a single unified governance layer. This 3D schematic represents the foundational layer of the new enterprise stack. This wide base is the governance bedrock. Databricks calls this Unity Catalog. It acts as the centralized governance layer for every single data and AI asset in the organization. It applies strict access controls, acting as the absolute filter for any user or AI request. This lineage tree maps out the origin of every asset. We trace a direct line from raw data to a machine learning model, right up to the end user. Sitting directly inside this governed foundation is the deployment layer, Databricks Apps. Developers deploy these serverless applications straight from Git repositories. Because they plug directly into Unity Catalog, they automatically inherit all the established permissions. Autonomous agents cannot safely execute workflows or modify enterprise data without these deterministic boundaries and observable lineage paths firmly in place. On top of that foundation, we add the second architectural layer. This drop-down tier is the predictive core, focused entirely on traditional machine learning integration. Legacy machine learning environments force data teams to use external orchestrators to move data in and out of models. Here, the process is native to the platform. Within this layer, MLflow handles the tracking of experiments and manages the complete lifecycle of every model in production. It also integrates OpenTelemetry traces. This records exactly how models perform over time, ensuring long-term AI observability. These trace logs are actively routed downwards, securely embedding themselves into the Unity Catalog base layer for permanent auditing. This predictive capability is also used internally. Tools like LakeFlow Jobs use AI to automate data layout optimization through a process called liquid clustering. For data analysts, SQL AI functions allow them to call predictive models directly inside standard SQL queries, applying complex math without leaving their workspace. Embedding predictive models natively into the data platform removes orchestration friction. It provides the mathematical engine autonomous agents require to make proactive decisions. To complete the backend architecture, this third layer stacks onto the predictive tier. This is the Generative AI and LLM Ops layer, powered by Mosaic AI. This environment provides the end-to-end infrastructure required to build and scale custom generative applications. A centralized control plane, the Mosaic AI Gateway, intercepts incoming API calls and routes them to either proprietary or open-source model nodes. The gateway handles all credential management and monitors usage across the different model providers. It supports high-performance hosting for advanced models, including GPT 5.2 codecs. To ensure accuracy, a vector search node pulls real-time context directly from the proprietary data store in the Unity layer below, feeding it upwards into the large language model. Developers also have access to the AI Playground, a secure sandbox for testing different models and refining prompts before pushing anything to deployment. Grounding generative models in real-time enterprise truth using retrieval-augmented generation prevents hallucinations. The AI responses are mathematically anchored to your actual data. Capping the 3D stack is the final layer, the conversational and agentic interfaces. The highlight here is Databricks Assistant, running in agent mode. Alongside the assistant is Databricks Genie. Genie democratizes data access by converting natural language requests directly into complex SQL queries. It can be embedded straight into endpoint applications like Microsoft Teams or Slack, bringing the data to where teams already communicate. But the core of the autonomy lies in the Databricks assistant and its agent mode capabilities. Given a macro goal, the agent builds a multi-step sequence, generating a notebook, identifying errors, and optimizing performance. During execution, it sends requests down into the generative and predictive layers below, fulfilling each subtask without manual intervention. Once the task is complete, AI and BI dashboards suggest the best visual formats to explain the resulting data trends to the user. This top layer moves the platform past a static tool you manually query. It becomes a dynamic engine that actively executes work on your behalf. Looking at this zoomed-out view of the complete four-layer architecture, we can trace the path from base data governance up through predictive, generative, and finally the agentic interface. Watch what happens when a single complex user prompt is entered. It cascades seamlessly downward through all four layers of the stack. The system triggers synchronized execution. It generates a predictive model, cross-references internal data via RAG, and logs the execution trace at the exact same time. Housing these capabilities on one platform allows data, models, and traces to move between layers without custom integration code or manual handoffs. These autonomous agents operate securely because they are strictly bound by the unified governance rules established at the base layer. This framework enables organizations to move from hosting disconnected models to deploying autonomous systems that operate within a single, governed environment. This single glowing node represents a standalone language model operating in isolation. In a production environment, a model isolated from enterprise systems lacks the context, safety controls, and reliability required to move beyond a simple chat interface. Taking a raw foundation model and converting it into a secure, proprietary system requires a massive operational shift. You have to surround that core logic with infrastructure that controls how it behaves. There is a vast gap between simple model hosting, just keeping a model online to answer chat prompts, and comprehensive LLM ops, which dictates how you test, route, and observe data interacting with that model at enterprise scale. To execute that shift, organizations rely on the Databricks Ada Intelligence Platform, which provides the architectural vehicle to manage the entire lifecycle of an AI application. To understand exactly what this infrastructure looks like, we are going to build a custom generative application from first principles, step by step. This infrastructure is the absolute prerequisite for advancing past basic chat interfaces toward autonomous AI agents that can plan and execute multi-step workflows. The security, routing, and governance of the operational pipeline surrounding the model defines its performance in an enterprise setting. This blueprint maps the start of our pipeline. On the far left, we establish our entry point, the developer. The developer first needs a sandbox environment, which Databricks calls the AI playground. Here, engineering teams can rapidly test and compare different LLMs and prompt configurations against each other before committing to a specific architecture. But selecting a model reveals an immediate limitation. This generic LLM has no awareness of your proprietary enterprise data. It only knows the public data it was originally trained on. To fix this, we move to Phase 2, contextualization. We pull from your raw enterprise data and run it through an embedding process. This embedding process translates documents, logs, and records into numerical vectors, a format the model can efficiently process. This data is stored in a dedicated vector search database. During a query, a technique called retrieval augmented generation, or RAG, actively pulls the relevant vectors and feeds them to the model. RAG acts as a critical bridge. It forces the AI to ground its responses in your specific enterprise reality, relying on hard internal facts rather than generic pre-trained weights. Grounding the model solves the context problem, but introduces a new vulnerability. Because the system now accesses sensitive enterprise data, it requires strict access controls. We secure this perimeter in Phase 3. This barrier is the Mosaic AI Gateway, acting as a layer of centralized control. The gateway handles core administrative functions. It manages all credentials and routes requests across different model providers, ensuring authorized queries are let through, while invalid requests are deflected at the perimeter. It also applies rate limiting and monitors usage across the system. This prevents external queries from overloading your infrastructure or triggering unexpected compute costs. With the access secured, we have to address the physical compute required to run these complex grounded queries at scale. This brings us to Phase 4. We transition the single compute node into a robust multi-server cluster known as Mosaic AI model serving. This hosting infrastructure is built to support high-performance demands. It handles both open-source models and large proprietary systems, like GPT 5.2 codecs, ensuring latency stays low regardless of the underlying engine. Pairing a centralized gateway with a high-performance serving cluster allows you to prevent data leakage without sacrificing enterprise-grade response times. The pipeline is active and secure, but we still face an operational hurdle: delivering this governed model to the end user through a functional interface. We achieve this through Phase 5, the deployment layer. Databricks Apps serves as the environment for launching these custom AI-powered applications. It uses a serverless architecture, pulling code directly from your Git repositories to seamlessly link your source control with the front-end UI. But deploying the app exposes a hidden risk in production AI. Because generative models are non-deterministic, tracing hallucinated outputs or logic errors through a complex pipeline is incredibly difficult. To solve this, we inject a foundational layer beneath the entire architecture. This is MLflow, providing total telemetry and observability. MLflow tracks experiments during development and manages the model's lifecycle through to production deployment. Specifically, it stores open telemetry traces from the playground, the gateway, the serving servers, and the deployed apps, giving you long-term visibility into the entire system. Without cross-pipeline telemetry, optimizing or debugging a generative AI application in a production environment lacks the necessary evidence for correction. Looking at this blueprint, we have successfully constructed a true end-to-end LLM ops pipeline. Yet there is one final overarching requirement. We have to ensure that data permissions and asset tracking are unified across every single node we just built. We achieve this using Unity Catalog. This serves as the universal governance layer for the entire architecture. Unity Catalog provides a single enforcement point. It applies fine-grained access controls and precise data lineage tracking to all assets, models, and databases simultaneously. This governed architecture provides the framework for transitioning toward Agentic AI. Autonomous AI systems plan and execute complex, multi-step workflows. You can only trust them to operate independently if their data access, their compute resources, and their telemetry are all centrally governed. We can see this in tools like the Databricks Assistant. When operating in agent mode, it can automatically generate notebooks, fix code errors, and optimize data performance without manual intervention. Ultimately, the final utility and success of any autonomous AI system rests entirely on the operational pipeline working silently beneath it.